Welcome to lecture series on advanced linear algebra. In my last class, we have discussed about the linear transformation from a vector space to another vector space. We have also seen the existence of linear transformations from a finite dimensional vector space to another vector space. And we have also seen applications, some more examples of the linear transformations. Now, let me see quickly, if I consider a function from a vector space to another vector space, is it necessary that always will have a linear transformation? For examples, suppose I have taken here T is a linear transformation from R2 to R3. So, my vector space capital V equal to R2 and W equal to R3. R2 means set of all these 2 points, I mean you can say xy plane. R3 means set of all 3 tuples, that is my Euclidean space. It is given that T of 1 1 equal to 1 1 0 and T of 0 1 equal to 0 1 1 and T of 1 0 equal to 1 2 1. We have to check whether such type of linear transformation exists or not. Okay. First we see that the set 1 1 and 0 1, it is a linearly independent set, linearly independent set please. And if I consider the 2 elements, another 2 element, that is 1 1 0, so this is my B, and let me consider B prime is equal to set consist of 1 1 0 and 0 1 1. Now, since this is linearly independent, then immediately I will say that by previous theorems what we have proved, there is a linear transformation. Suppose this is my alpha 1 and this is alpha 2 and this is my beta 1 and beta 2, then we know that there exists linear transformation from T of from R2 to R3 such that T of alpha 1 equal to beta 1 and T of alpha 2 equal to beta 2. But here we have another condition, that 1 0, which is basically your linear combination, that is alpha 1 minus alpha 2. Okay. So, I am getting this ones, and but image of T 1 0, suppose this type of linear transformation is possible, then image of T 1 0 should be equal to T of alpha 1 minus alpha 2, which will be equal to T of alpha 1 minus T of alpha 2. But this is okay, this is equal to how much? T of alpha 1 is equal to beta 1, that is equal to say 1 1 0 and minus 0 1 1, which is equal to 1 0 minus 1. So, image of T 1 0 is like this, but to given condition, image of T 1 0 equal to 1 2 1, which is not equal to 1 0 minus 1. So, such type of linear transformation does not exist please. We can see many more problems in the assignment sheet also. Today I will discuss about the one term called rank of T, the concept of rank. In last time also I have discussed the concept of range space, null space of a linear transformation, and we have seen that the range space is subspace of the corresponding codomain space of the linear transformations, whereas null space is the subspace of the domain space of the linear transformation. And we have also defined what is rank of T as a basically I have defined dimension of the range space of the linear transformation, whereas nullity is basically dimension of the null space of the linear transformation. Now, we want to see, does there exist any relation between rank and nullity of a linear transformations? There exists any relation between rank of a linear transformation and nullity of that linear transformation? That's the questions. Answer is yes, we have relation, but for certain case, I mean with some conditions that it is like this, it is small theorem type. Let T be a linear transformation from vector space V into W, where V and W are defined over the field capital F. If dimension suppose dimension of V is finite, then rank of T plus nullity of T equal to dimension of V. I mean to say, dimension of the range space of T plus dimension of the null space of T equal to dimension of the V place. Here I am not talking about the dimension of W, it may be finite, it may be infinite, but we are basically emphasizing on the dimension of the V place. So, let me give a proof. So, this is the basically condition for which there is a relation between rank and nullity of a linear transformation T. Let NT represent the null space of T and RT represent range space of T. Certainly NT will be subset of V. Let the dimension of V is n. Since given to us it is a finite, so I can say the dimension of V is say n. So, dimension of NT is also finite and less than equal to n. Let B equal to alpha 1, alpha 2, alpha k be an order basis of null space of T and T. So, by extension theorem, B can be extended by including n minus k more linearly independent elements of V to be a basis of capital V. So, let me consider B star, which is consisting of alpha 1, alpha 2, alpha k plus 1 and alpha n be an order basis of capital V. So, T of alpha 1, T of alpha 2, T of alpha k, T of alpha k plus 1 and T of alpha n. So, this set will span the range space R T, because any element of V can be written as a linear combination of alpha 1 to alpha n. So, any element in the range space will be linear combination of T alpha 1, T alpha 2 and T alpha n. In fact, T alpha I equal to 0 for I equal to 1 to k, since alpha 1 to alpha k are in NT null space. So, according to the definition, T alpha I equal to 0, I equal to 1 to k please. So, T alpha k plus 1, T alpha k plus 2 and T alpha n will span the range space R T. So, this is n minus k elements are basically which span the R T place. Claim it is also a basis of. So, to be a basis, we know it has to span the space R T and it has to be also linearly independent. Already you have seen T alpha k plus 1 to T alpha n span the range space T. Now, to show it is a basis, I have to basically show this T alpha k plus 1, T alpha k plus 2 and up to T alpha n is a linearly independent sets. So, now to show T alpha k plus 1 to T alpha n is the basis of R T, we have to show it is a linear independent set. Suppose not, suppose it is not linearly independent, suppose it is not a linearly independent Li set. So, means that it will be linearly independent. There exists C I equal to k plus 1 to n belongs to your field capital F such that sigma C I t of alpha I equal to k plus 1 to n equal to 0, where not all C I are 0. So, this implies T of sigma C I alpha I equal to 0. This is because from the definition of T only we have like this. This implies that I equal to k plus 1 to n. So, this implies sigma C I alpha I equal to k plus 1 to n belongs to the null space, because according to the definition of null space. So, I have sigma I equal to k plus 1 to n, C I alpha I will be in the NT place. So, since it is element of NT, so I will be able to express as a linear combination of the basis element of NT. So, it means this implies there exists D1, D2, dk belongs to F such that sigma di alpha I equal to 1 to k equal to sigma C I alpha I equal to k plus 1 to n. So, this implies that one can rewrite sigma di alpha I equal to 1 to k plus minus C I into alpha I equal to k plus 1 to n this is equal to 0. But alpha 1 to alpha n is a linearly independent set. So, this implies that each di equal to 0 for I equal to 1 to k and C I equal to 0 for I equal to k plus 1 to n. This contradicts that in the very beginning we assumed that not all C I are 0. Hence, T alpha k plus 1, T alpha k plus 2 to T alpha n is a linearly independent set of RT. This implies rank of T plus nullity of T equal to rank of T equal to how much, that is n minus k plus nullity of T is equal to plus only k. So, this is equal to n, which is equal to dimension of V please. So, we have seen that rank of linear transform T plus nullity of the T equal to dimension of the V. See, if the dimension of V is not finite, can I conclude like that? So, in that case we cannot do it please. If the dimension of the V is not finite, then we cannot conclude like this type of conclusion please. Okay, so we have seen what do you mean by rank of a linear transformation. Soon we shall see the linear transformation is nothing, it is basically give me some matrix please. So, it will have a matrix structure please. So, we have seen the meaning of the rank of T. Now, let me introduce the concept of rank of a matrix. We have already defined row rank of the matrix. So, let me recall and give similar definition of the rank of a matrix, and let us discuss that please. Let A be an m cross n matrix over the field capital F. Let rho 1, rho 2, rho m be the first, second and mth row of matrix A. Let beta 1, beta 2 and beta n be the first, second and nth column of matrix A, please. Let W 1 is basically linear span of rho 1, rho 2, rho m, whereas W 2 which is equal to linear span of beta 1, beta 2 and beta n. So, W 1 is the row space of A and W 2 is the column space of the matrix A, please. Dimension of W 1 is called as row rank of matrix A and dimension of W 2 is called as column rank of matrix A, please. Okay. Then row rank of A is equal to column rank of A. So, this is a problem I have considered. It is basically I have considered M cross N matrix, and I am basically showing that for a M cross N matrix defined over the field say capital F, row rank of A equal to column rank of A. So, it is a proof type. This is some sort of lemma type we can say. I will apply the above results like this thing. Okay. So, consider T is a linear transformation from F n cross 1 to F m cross 1 defined by T of capital X is equal to A x. I have already mentioned F of n cross 1, it is basically space of column matrix of n cross 1 order, and F of m cross 1 is basically space of column matrix of m cross 1 order, please. They are all vector spaces over the capital F. So, I have defined a linear transformation T from F n cross 1 to F m cross 1 by T of x equal to A x. Okay. So, this implies for any y belongs to R T, there exists x belongs to F n cross 1 such that your A x equal to y, but A x is this is something like this x 1 x 2 x n equal to say y 1 y 2 y m, some these things. This is your AIJ matrix. So, this means that this will be basically x1 into the first column. So, I can write down this is A1 plus x2 into second column of the matrix say A2 plus xn into nth column of the matrix A please. Here A is m cross n, this matrix please. So, I can say that this is equal to your capital Y. So, this implies range space of T is a subspace column space of A. Also, column space of T is a subspace of range space of T, because if I take any linear combination of the column of this A, that is basically it is writing AX. So, it will be in the range space. So, this implies okay. So, this implies what column space is equal to range space, range space. So, this implies column rank equal to rank of T. So, column rank equal to rank of T. Okay. Now, if I see the null space of this, the null space of T is basically what? Solution of the system Ax equal to 0. So, let capital S denote solution space of Ax equal to 0. So, this implies that my NT is equal to S. This implies that null space of T is basically capital S. Okay. So, this implies by the previous theorem, which I am saying also rank-nullity theorems. Previous theorem says that a rank of T plus nullity of T equal to dimension of the space V please. So, this implies column rank of A plus, because column rank of A is equal to rank of T plus nullity of T equal to dimension of V, or column rank of A plus dimension of S equal to dimension of V please, is equal to n please. Okay. Again we know if row rank of A is say R, then dimension of solution space of Ax equal to 0 is what? So, in this case the dimension of the solution space of Ax equal to 0 will be number of free variables. Since A is a m cross n matrix and if row rank of A is R, then number of free variables will be n minus R. Is n minus R. So, this implies dimension of S is equal to n minus R. R is what? R is basically row rank. row rank of A please. So, we have, if I substitute this one in previous expressions, this is my 2 and in previous equation this is 1. So, we have that, so column rank of A plus n minus row rank of A equal to n. So, this implies that column rank of A equal to row rank of A. So, this is very interesting results for a M cross n matrix defined over a field capital F. The row rank of the matrix is equal to column rank of the matrix also. So, we have seen that for a given M cross n matrix, the column rank of the matrix equal to row rank of matrix please. Now, let me take an example and see. See, here I have taken a function t from f3 to f3 defined by for any n 3 tuple x1, x2, x3 which is mapping to x1 minus x2 plus 2x3 comma 2x1 plus x2 comma minus x1 minus 2x2 plus 2x3. So, this is the definition suppose, and then I raise two questions. The first question is, if ABC is a vector in F3, what are the conditions on ABC that the vectors be in the range of the T please? And part of this question, what is the rank of the transformation T, and second is what is the condition on ABC so that ABC will be in the null space of T please. So, let me answer one by one. Okay. So, we want to know under what conditions on ABC this will be in the range space of ABC. See, so ABC will be in range space RT provided there exist x1, x2, x3 such that T of x1, x2, x3 equal to ABC. So, this implies that what? So, this implies that x1 minus x2 plus 2x3 equal to A, 2x1 plus x2 equal to B, and minus x1 minus 2x2 plus 2x3 equal to C. So, this condition has to be satisfied because T of x1, x2, x3 is given in star. So, I have used that definition and I have these three equations. So, ABC will be in the range space of T provided this system has solution please. So, this implies that if I write down 1 minus 1 2, if I write in augmented form, then A 2 1 0 B minus 1 minus 2 plus 2 and C. Now, I have to check whether the existence of solution criteria is satisfied or not. So, let me go for the elementary operations. For this I am getting, say if I do it first row I will keep as it is 1 minus 1 2 A. Second I am replacing basically R2 is equal to R2 minus 2 R1. If I do it, so this is going to be 0. Okay. Second row the first entry is 0 and 1 minus 2 is equal to 3 and then 0, this is a minus 4, then B minus 2A. And third row is going to be just if add R3 is equal to R3 plus R1. So, if I replace R3 by R3 plus R1, then I am getting 0 minus 3 plus 4 and here I am getting A plus C. Okay. Well, so one more iteration is required. I mean one more step. So, I will have 1 minus 1 2 a, which is 0 3 4 b 4, okay, minus b minus 2 a. Now, if I simply add second and third, so I will have 0 0 0, I will have b minus a plus c, b minus a plus c. Okay. So, this implies for existence of solution, we need b minus a plus c equal to 0. Although I have not made this matrix as a row reduced echelon form, but I can immediately see the first and second are linearly independent, and so I no need to proceed for the next step or to find basically the rank of the given matrix. So, rank of the given matrix is equal to, it is obvious, it is 2, because first and second row is basically linearly independent place. So, this implies that A has to be equal to B plus C. So, this is the required condition for any 3 tuple A B C to be in the range space of the linear transformation T here. Okay. And so, rank of T equal to, rank of T is equal to 2, because we have 2 linearly independent rows. So, that will basically give the row space of the given matrix, or I can say that. So, this will basically act as a basis for the linear transformation please T, basis for the range space of the T please. Rank of this matrix here, and since the here I am getting 2 linearly independent rows. So, this means that row rank equal to 2. So, row rank equal to 2 means column rank also of that same matrix equal to 2. So, I can say that rank of the T is equal to 2. Now, ABC will be in NT null space provided T of ABC will be equal to 0. So, T of ABC equal to 0 means this implies that A minus B plus 2C, A minus B plus 2C equal to 0, 2A plus B equal to 0, and third minus A minus 2B minus A minus 2B plus 2C has to be equal to 0. So, this is the criteria for the point ABC will be null space of the linear transform T please. Indirectly you can say that solution space of the system equal basically, this is basically 1 minus 1 2 2 1 0 minus 1 minus 2 2. If we solve this system like A B C, if you consider this system, so we are looking for the solution of this system please. So, this means that the solution of this system is basically equivalent to, so we can see that if you consider the row reduced echelon matrix, corresponding row reduced echelon matrix is your 1 minus 1 2 0 3 minus 4 0 3 minus 4. So, 0 0 0, looking for the solution of this system please. So, this means that A minus B plus 2C equal to 0, other one is 3B equal to 4C. So, this is the required condition for ABC to be in the null space of linear transform T please.